Here are the audio notes for the 5 basic reaction types. The first one being a synthesis reaction. This is when you have multiple reactants, I say 2, but it could be more than 2, coming together to make one product. An example would be magnesium plus oxygen making magnesium oxide. Now, depending upon when this is done in class, maybe you'll get to see some of these demonstrations done. But otherwise, what I'd ask students to do right now is to write out the formula version of this. So if here's a word equation, I want you to write the formula equation. Feel free to pause the video in order to check or give yourself a chance to figure this out. Right here is what I'd start with, the formula for each, and then I'd recognize that my oxygens are not balanced. So to balance my oxygens, I would need to put a 2 in front of the MgO. 2 oxygens, 2 oxygens. But now my magnesiums aren't balanced. So I would have to put a 2 in front of the magnesium. If you were to see this reaction, magnesium is a silverish metal, oxygen is a gas at room temperature, and it makes a white ashy substance, the magnesium oxide. The next type of reaction is called a decomposition reaction. A decomposition reaction is the exact opposite of synthesis reaction. Where a synthesis, you make one thing, in a decomposition, you start with one thing. Decomposition reaction that's pretty common to discuss is hydrogen peroxide breaking down into water and oxygen. Once again, feel free to pause the video. I want students to try to write this out in the formula format. Here is what's called the skeleton equation before balancing. Since hydrogen peroxide is a solution, I use AQ. Water is a liquid, oxygen will be a gas in this case. Notice how the oxygens are not balanced. 3 oxygens on the product side, 2 on the reactant side. First thing I'm going to do is put a 2 in front of my water, making this odd number of oxygens turn into an even number of oxygens. From there, I can put a 2 in front of the hydrogen peroxide as well, and my equation is all balanced. A lot of things do not decompose on their own. A catalyst is required. A catalyst is defined as something that will help speed up a reaction. A catalyst was actually brought up when we talked about our rate of reaction. We'll go over that more when we get to activation energy curves. However, if I go back to my equation now, it's pretty common. In this case, a catalyst for this decomposition would be a potassium iodide solution. To write the catalyst above the arrow to show that it's involved in the reaction, but it's not actually a reactant or a product. The cool thing about a catalyst is it's there, but it doesn't get used up at all. So once again, that was a decomposition reaction, the exact opposite of a synthesis reaction. Single displacement, or sometimes called single replacement reactions, are a little more special. In a single displacement reaction, a single element reacts with a compound to create a new element and a new compound. Not every time you try to perform a single displacement reaction does it occur, however, and that's why we're going to be doing a lab next class specifically on single displacement reactions. So, the single element to start with must be more reactive to replace that within a compound. Remember back to first semester, we talked about things like fluorine being more electronegative, is more reactive than chlorine, for example. There is something next class that I can introduce to help you with identifying what's more reactive than something else. For now, a reaction that I would again like students to write down in formula format is copper metal plus silver nitrate solution, making silver metal and copper 2 nitrate solution. And feel free to pause the video to give students a chance to write down these formulas. Original equation would look like this: copper solid, silver nitrate solution makes silver solid and copper nitrate solution. Notice that there's a 2 because this is copper 2 nitrate. That means we have 2 nitrates on this side and only 1 nitrate on this side. Sometimes when balancing equations, it's easier to just identify how many of each type of polyatomic ion is on each side. In this case, in order to balance it, I need to put a 2 in front of my silver nitrate, because now I have 2 of the NO3s on both sides. However, now I also need to put a 2 in front of my silver to make sure that is balanced. This would be a properly balanced single displacement reaction. Notice that it's one element in a compound, typically an ionic compound, metal, non-metal, making a new element in compound. The copper is trading places with the silver. Copper would not trade places with nitrate because copper being a metal would replace silver, which is a metal. Next type of reaction is called a double displacement reaction. This is when we have two ionic solutions, and there's going to be a switch that occurs in it. Just like single displacement, double displacement reactions don't always occur, and they have to abide by special rules that we will go over in future class periods. But to kind of give you a brief introduction to that, double displacement reactions only happen if the two reactants are soluble, which means they're both solutions, and one of the products is not soluble. Example that I want students to write down is sodium chromate solution plus silver nitrate solution, making sodium nitrate solution in silver chromate solid. Once again, pause the video, give students a chance to write out this in formula format, and then we will show the answer. A little harder to fit this entire equation onto the sheet, but here is one solution plus a second solution, making a new solution and a precipitate, a solid. Just like in the lab, we've made precipitates before. You're going to be doing this more in the coming class periods. Once again, all these aqueous show that it's a solution. I do have to balance this out, however. Notice that there's two silvers here. I'm going to put two silvers there. Now I have two nitrates. Two nitrates, two sodiums, two sodiums. This equation is now balanced. When it comes to recognizing this type of equation, it involves two ionic solutions, so two compounds making two new compounds. The Na switches places with the Ag. Now when you do that switch of place, just like with the single displacement, you have to rebalance formulas. Silver's a +1 charge, chromate's a -2. That's why it's Ag2CrO4. Just like in the previous problem, AgNO3, CuNO3 2. So a very common error that students make when writing these equations is they don't rebalance formulas. So even though you know the switches, Na is trading with Ag, you have to rebalance formulas. Last thing to note on this slide, by the way, next unit, our advanced reaction types unit, will involve three different types of reactions, one of which is called an acid-base reaction. Acid-base reactions do fall in the category of double displacement. Last type of reaction is a combustion reaction. This is a special type of reaction that is involving burning, and we try to simplify it just to include carbon-hydrogen compounds, which is also called a hydrocarbon. In the burning process, these carbon-hydrogen compounds will react with oxygen in the air to produce water and carbon dioxide. An example that is often fun to do, even on a lab bench, because the lab benches can handle this, is squirting a little bit of hexane, that non-polar solvent that we used last unit, on the lab bench and lighting it on fire. Once you light it on fire, it's going to react with the oxygen in the room. So once again, if hexane and oxygen are the two reactants, and every combustion ends in CO2 and H2O, let's have students take a minute to try to write out this reaction in formula format. Hexane is a pure liquid. It would be tricky to be a solution, so watered down, and then be able to light it on fire. Oxygen is a gas. H2O could be a liquid or a gas. It just depends on what's left over at the end. This equation, much more difficult to balance. I would start with the fact that I have 6 carbons here. Let's put a 6 in front of here. 14 here means I need a 7 in front of my water. But let's add up my oxygens now. 6 times 2 is 12. 12 plus 7 is 19. We are not allowed to use decimal values for coefficients. So what we have to do is actually get rid of all these coefficients and double the entire thing. If I put a 2 in front of here, I can then put a 12 in front of my carbon dioxide, 14 in front of my water, and a 19 in front of my oxygen. This is the one type of reaction that has the same products every single time, carbon dioxide and water. So that's one way that you can identify this particular reaction type. Also, it starts with a carbon-hydrogen compound, another way that you can identify this reaction type. And that's the very last thing that I note on this slide.